ideal current and voltage characteristics of MOSFET devices. You see, for example, in the um, if you recall, these characteristics are in the saturation region, SAT region, and these are quadratic relationships with respect to the gate source voltage and the current. And similarly, we have this in the NMOS device as well. So NMOS, PMOS devices are very similar characteristics. And then there is a conduction parameter Kp and Kn associated with these devices. So you see that in both the saturation regions of these devices, we have a quadratic nature of IV characteristics. Okay. Um, but these assumptions, similarly, you see in these non-sat regions. Okay, the gate source voltage has a almost linear characteristic uh, with the drain current, okay, drain to source current, and a similar equation follows for the NMOS device as well. This is what we have discussed previously. So these characteristics are valid if the channel length is greater than 2 micrometers. So we have been considering the a longer channel lengths, but the question is what happens if the channel length, this capital L, channel length is small. Okay. Now, for example, this is a PMOS device over here. Okay, in which you understand that you have since you for a PMOS device you need a uh, negative supply at the gate so that you can create a space charge region of P mobile carriers. Okay, so there are holes here. So P this is P positive. Okay, and this is P positive, and this is going to conduct. This is a PMOS device, so it will have positive, positively charged particles. Okay, so there is an establishment of an electric field such that this electric field is perpendicular to the inversion layer. Okay, this is the direction of the electric field. This is one electric field. The other electric field, so one electric field is being established by your gate voltage. The other electric field is being established by the drain voltage. Okay, the source is kept at the ground. So you see this is as such so that it moves the charges. Okay, it moves the charges from positive to negative. So the electric field in the channel due to VST is horizontal. Okay, it is in this direction, positive to negative. Okay, so you have horizontal electric field adjacent to the channel length, and then you have a vertical electric field due to the gate supply. And these two fields they interact. Okay, for long channels it's not important. I mean, you have these ideal characteristics, but these current voltage relations for NMOS and PMOS, which are ideal relations for long channel devices, this doesn't hold if you have a channel length of 0.2 micrometers or less. Okay, so in these devices, you see the horizontal electric field in the channel is induced by the drain voltage, and the vertical electric field is induced by the gate voltage. And well, in these devices, you can treat them independently. There is no interference for long channels. But if the channel length is short, like 0.2 micrometers or less, well, they do interfere. Okay. So what happens is the first parameter that is going to change is your threshold voltage. Okay. The threshold voltage in here in uh, PMOS and NMOS will become a function of the channel length. Okay, so you see the one of the several effects in the short channel devices that influences and change the long channel current voltage characteristics is the threshold voltage. Okay, so threshold voltage is a function becomes a function of channel length. So this variation must be considered in the design and fabrication of these devices. You see the threshold voltage that is required to create the minimum voltage, gate voltage required to create the inversion layer to turn the device on for the conduction of charges, positive or negative, from source to drain. You require a field, you require a gate field to establish that channel, and that is for enhancement MOSFET. So, uh, well, that voltage is not only being dependent on the electric field, the minimum electric field that you need, but the threshold voltage is also the function of the channel length now. Okay. The other thing is that since in the small channel lengths, the two fields horizontal and vertical fields, they interact, they become dependent. Okay, so as you increase the drain voltage, as you increase the drain voltage, the threshold voltage becomes even small. Okay, so as the drain voltage increases, the effective threshold voltage decreases. This effect also influences the current voltage characteristics. Well, one way to understand is that, you see, if you have a small channel, increasing the drain voltage, okay, is going to reverse bias this junction. Okay, so this is p doped semiconductor region in the drain, and this is negative. So this p-n junction, well, you're going to reverse bias it. So this depletion region is going to increase over here, and what you're going to do, the effect will be that you're going to pinch off the channel around the gate terminal, and the channel will be tapered off, as we have seen before. Okay, so basically you're saturating the device over here, okay, such that increasing VDS then won't help in increasing the drain current. So this threshold voltage is now complicated. Okay, it's also depending on the it's also dependent on the drain voltage. Okay, and it is also dependent on the length, which is small, 0.2 micrometers or less. Okay, so it's not only the minimum voltage required to produce an inversion layer, but it also depends on what the drain voltage is. Okay, increasing the drain voltage, increasing the drain voltage will lower your threshold voltage. Okay, you need even less. So so the process conduction parameters, similarly Kn and Kp, if you recall, um, you remember it in these conduction parameters, Kn and Kp. Kn and Kp were those had the geometric parameters W by 2L, and then there were process conduction parameters for PMOS. This is mobility of the holes, mu p, and then you have the oxide capacitance COX. Similarly, for this is Kp. Okay, this is the conduction parameter. But the electrical parameters or the process parameters, this term is your Kp. Okay, you see, we kept this constant. Okay, and this mobility had no dependence. We didn't assume any dependence of this mobility of the charge carriers with respect to the gate field. But if the channel length is small, so the process conduction parameters, they become directly, since they are directly related to the carrier mobility, and we assume the mobilities and corresponding production parameters constant. Okay, over here mu n and mu p were kept constant. The carrier mobility values are now also the function of vertical electric field in the inversion there. Okay, so as the gate voltage and the vertical field increases, the carrier mobility decreases. All right, because you see this horizontal field, which was independent in the larger channels, is trying to is giving the driving force for the charges to travel from source to drain and conduct the current. But now this vertical field is, since it is not independent, it's now going to interfere with the horizontal field. Okay, so increasing the vertical field is going to interfere with the horizontal field, thus reducing the current. So again, your current to your drain current characteristics, which are being dictated by these equations for ideal long channel, they no longer hold for short channels. Okay, so the story is different. Okay, so you see, as the gate voltage, it says over here, the gate voltage, as the gate voltage and the vertical field increases, the carrier mobility decreases. Okay, thereby decreasing the conduction parameters K and Kp. So this result again influences your current voltage characteristics of the device. Okay. Similarly, another effect um, that occurs in short channel devices is the velocity saturation. So as the horizontal electric field increases, the velocity of the carriers reaches a constant value and will no longer increase with an increasing drain voltage. Okay, so that means your VDS saturation is going to decrease. So the drain current will reach its saturation value at a smaller VDS. So now the drain source voltage, which establishes the horizontal field, will result in a lower drain to source saturation values for each VGS curves. So this, for example, this point is going to shift towards left. We're going to have lower saturation value. So these black dots are going to shift towards left because of the velocity saturation. Okay, and this and then and since you are going to reach, you will have a smaller linear regions. Okay, I mean this these points. So maybe the saturation starts over here somewhere earlier. So that means your the region in which you can use your in linear region which you can use MOSFET as an amplifier with the short channel effects. This region is small. Okay, you cannot use this as an amplifier. You can use this as an amplifier for a very small linear VDS and ID region. Okay, the region becomes small. So this is due to the velocity saturation. So the drain current also becomes approximately a linear function of the gate voltage in the saturation region rather than the quadratic function of the gate voltage in the long channel characteristics. So you see, in the saturation region, we had this. These are the saturation region for NMOS and PMOS devices. So not only your threshold voltage is now a function of channel length and VDS, but your drain current is no more a quadratic function. It's no more a quadratic function of the gate source voltage. Okay, so the characteristics are altered. You see, if you are going to consider these current voltage characteristics, these current voltage characteristics for short devices, well, the current volt characteristic will be different. Okay, but these are for long channels. So these are for long channels. So these parameters they should be assessed and should be kept in mind while using this as an amplifier or for DC biasings if your channel length is small. Okay, but for these introductory text introduction for MOSFETs, well, it is safe to assume long channel ideal IV characteristics um, without without losing the generality of these curves. Okay, but these short channels, they must be kept in mind. If you have a small channel, then your threshold voltage and your electric horizontal and vertical fields, since they are not independent, so everything is going to change from the threshold voltage to the IV characteristics and to the saturation voltages. They will become small due to the saturation. Velocity saturation mobility is going to change. Mobility of the charge carrier is going to change due to the gate source electric fields. Okay, so these parameters one should keep them in mind while designing MOSFETs for very large scale integrated circuits. Okay, if you are going to put them in a very in a very large scale integration with small sizes.